Hello everyone, good afternoon. It's time for class again, and this is ECE341, the probability course. Today we will discuss the reliability problem. When you have something combined by several components, and each components they have kind of probability to work well or get something wrong, then you want to know the reliability of the whole part, the whole machine or whole process, right? We call this a reliability problem. Yes. Okay. I already write something here. Reliability analysis. All right. You can consider like this. We have, for example, we have a kind of network of the power supply. You consider electric power supply network. Then you have most simple one. You have a plant to create. This is a created power, right? Creating plant. And then kind of you need you go to somewhere like this is your house, things like this. Okay, so here then you can think like this one with probability P to work well. Yeah, the plant maybe get something wrong, right? So may work well, may get something wrong. So they have a probability here. And each wire, you have a network, right? They have both. They have probability like a Q work well. Then we want to know the probability you have power, have the electric power. Well, we want to know this. Okay, now this is a kind of thing, you have three parts you need to consider. Here, and here, right? You have three parts you want to consider. So when it will work well, if all of them work well, then you can have the power. Any one is a kind of a broken or something wrong, then you are lost your power. So this one equal to, I say this is A, this is A, this is a B, this is a C. So this one equal to probability both A and B and C. All of these three works. And of course we can suppose they are independent. Independent. They were not related to each other. Then we have this probability because they are independent, and then they are the probability A times probability B probability of C, and they have P and Q squared. Okay. So this is one example. And we can also consider the things work like this. The same thing, but the connection is different. I have two wires, two lines to connect. Two wires to connect. Two wires to connect. And here is also Q, same use Q, Q, and this is P. Then you have power will be, now you have two paths, right? Two paths. So anyone works will be fine. I see this is a path L1, this is path L2. So this will be L1 union with L2. Okay. L1 will union with L2. Okay, if you want to calculate these, it's a union, so there will be PL1 plus PL2 and minus PL1 times L2, intersection with L2, right? We have this formula in the theorems part. Okay, so PL1, similar with that, is this one has a property P and the Q, so PQ squared. And another is also PQ squared. And we need minus both works. Minus both works. So all of them, they are good. There will be PQ force, right? All of these are working well. So we have these. It could be 2PQ squared minus PQ force. So this will be the answer. This will be the answer. Usually this will be better than that one, right? You have one more line, one more path. We call this kind of things is a redundant network. That means, you know, we have some actual wire, actual part, but it can protect the user, has more kind of more reliability, right? Provide more reliability, even some part getting wrong, but they are even one pass getting wrong, then another pass can still work. Yeah. The value can do a try which one larger. Suppose like P equal to Q equal to 1/2. Just an example, you know. Usually this should be a number close to 1. Right? Most time it works well. Here just an example. Then I have these PQ square will be 1/8, right? 1/8. And this one, P equal to Q equal to 1/2. This one will be, this one equal to 2 times 1/8 minus, this will be power 1 over 2 to the 5. 2 to the 5 is what? 3, then 16, 32. 32. Okay, what it is? This will be 0.125. This will be, 2 of these is 1/4. And minus 1/8 is this, 1/16 and 1/32, right? This one, minus 0.03125 equal to 0.25 minus 3, I get 2, and give 1 to the following, so it's 1. And 1 I get A75. Yeah, the property is. So yeah, obviously it's better than the just one pass, right? Yeah. Okay. So things like that. So here we have two concepts. One is we call it a cascade connection, right? This is a cascade connection. It's a cascade connection, right? One followed by another one. And here we have two paths. Each path is cascade connection, but these two paths, these two put together, this is a parallel connection, right? This is parallel connection. Parallel connection. All right. And the calculations are different. For the cascade connection, if the whole path work, that means each part will work. Each part, all of them, they have to work. So here's the intersection. All of them now work. And the parallel way, we have two paths, right? Two paths, they connect the parallel way. So the whole thing work equal to one work or the other one work. So here I have upper and lower two paths. So it is upper load work or upper bound work or the lower bound work, right? So need both. It is a union. You see, this cascade connection here is an intersection, and parallel connection, this is a union. There's a union. When you connect calculation, you need to use both. You need both, depending on how to build the whole thing. Yeah, and write this one. This is a parallel. This is a cascade. Cascade connection. This is A1, A2, A3, and the probability of AI works equal to PI, and this is the overall one. Overall one, I call this as B. Okay, B. Then B works were equal to all of these three works, and then there will be a 1 work, a 2 work, and a 3 work. It will equal to a 1 work times a 2 works and a 3 works. Right? I write this way. Yeah, I write A means it works. If it doesn't work, I put C, a complement. It doesn't work. A equal to A works. Alright, yeah, this way. Okay, from here to here, actually, basically, you need an assumption. Assume AI, AJ independent. Yeah, if they are independent, you can separate them. If they are related, then things might be more, definitely it should be more complex. Right? So here we just suppose they are independent. Yeah, A1, A2, A3, independent. Okay, this is a cascade connection. And each one is a PI, then this is a P1 times P2 times P3. Okay. And for the parallel connection, it looks like this. Yeah, I put 3 here. Maybe you have more. Right? A1, A2, A3. Right? Look at this. And suppose the whole thing, I still use B to denote the whole material, the whole process or whole machine or something. Then, if P AI equal to probably A PI, I equal to 1, 2, and 3, then probability of B will be the union of them. Right. The union of them. Then what is the probability of these? If you use the formula looks like this one, we have used this, right? We have formula look like this. The union of these two equal to the, you need to add them together and the minus intersection of it. So we have this as a 0. So here we can calculate this one right here. Probability B equal to probability of A1 plus probability of A2 plus probability of A3 Now we have 3 of them, so I need a minus A1 and A2 minus the probability of A2 and A3 and minus probability of A3, A1, any 2 of them, right? Any 2 of them minus, and plus the whole thing, the whole intersection, A1 intersection with A2 with A3, and you write in this way, right? This way. Of course, you can write it out. This is a P1 plus P2 plus P3 minus P1 P2 minus P2 P3 minus P3 P1 and plus P1 P2 P3. Now you can have the formula looks like this. And okay, so this is for 3 components, right? 3 components. If you have more, like you have 10th components, can you have these? Yes, we still can have this one, but it will be longer. You need each one, the minus pair of them, all the pair of them, and plus all the 3 of them. Okay, because you have more, then you need to keep working on minus all the 4 of them, the probability of any 4 of them, and then plus all the probability of 5 of them. Then minus plus minus plus, you do the thing until the last one will be, suppose you have 10, then last one will be 10 of them times together. That will be very long, very long. So we can have another way to calculate. This is what? This is a probability of B doesn't work. Doesn't work. AC equal to A doesn't work. Alright, so A, that means A works, and AC means A doesn't work. I use this notation. So BC means the whole thing doesn't work. In which case it doesn't work? This is a 1 minus PB, right? And what is it? No, sorry. 1 minus PC. Yeah, this is PB. So 1 minus PBC. PBC means it doesn't work. Alright, now it works. I'm sorry. I go to that's wrong. This is 1 minus this one. And then what is this one? This one doesn't work. Now though, any one of it works, then B works. Any one works, then B works. So only when all of them they do not work, you have this BC. So all of them do not work. So this one will equal to 1 minus P1 times P2 times P3. That's it. This is quite simple. This is quite simple. Right? We can double check whether this is correct. Whether this is correct. Oh, no, this is BC. Yeah, and each one will be 1 minus P1 times 1 minus P2 times 1 minus P3. Actually, these two are same. These two are same. We can check. We can double check. 1 minus P1, 1 minus P2 times 1 minus P3 are equal to 1 minus, I times these two together, I get 1 minus P1 times 1, right? And minus P2 plus P1, P2. Okay? Negative P1 times these two, I get these two. Okay, this times 1 minus P3 equal to 1 minus 1 times it, the whole thing times 1. I write this. So it's 1 minus P1 minus P2 plus P1, P2. And the whole thing times negative P3. So negative P3, negative P3, 1 P1, P3, and negative times another negative P2, P3, and the negative P1, P2, P3. You see? Okay, after you subtract these two, I have P1 plus P2, right? The 1 cancel. And I use and another P3, right? The single term. Then the second order term, P1, P2, P1, P3, P2, P3. So it's P1, P2, P2, P3, and P3, P1, right? And the last term is this is plus, this is minus. It's minus, minus, minus. And then this is minus, this is plus. So it's a plus. Minus, minus, plus. P1, P2, P3. Okay, I got this. Alright, are they same? This one? And this one? Yeah, they are same. Okay, so this is for parallel connection. We can calculate by this way. This way. We do not need to write so many terms, right? This is just you times them together, you get it. You get it. Alright. Okay, we can consider an example. Actually, I have two examples here. Alright. Example 1. We have an operation consists of two redundant parts. So that means we have two, right? One is this, one is this. Then we only need one can keep the system works. But now I have two paths. Right? You suppose like you have power supply. The power will go along two paths, upper bound and the lower bound. So we call this is a redundant, right? Redundant. We have extra more for the safety, for the reliability. Right? The first part has two components in series. Okay, so in series I have W1 and W2. So here, this part we separate as two parts. And the second part has two components in, it's also in series. Okay. It's W3 and W4. And our component success with probability P. So PWI equal to 0.9. That means PWIC will be 0.1, right? So success means have 90%, and something wrong is 10%. Then we want to know the whole thing. I say this is a B. I want to know the probability B. B is the whole operation works well. Yeah, whole operation can work. So what it is? I gave name. This is L1. This is L2. So probability of B or equal to probability L1 and L2. Right? L1 success or L2 success. So it's a union. And this one equal to, I prefer use another way. It is a 1 minus probability BC. That means something wrong. So this one equal to 1 minus. Yeah, I don't use this calculation. I can still use this one. I use this formula like this, but now I prefer like use this way. So 1 minus PBC. PBC, that means P L1C and L2C, right? Both getting wrong. Now both getting wrong, then the whole system will wrong. Okay, and L1C. So L1C was if this one block or that one block, but I use L1. This is a 1 minus PL1. I write in this way, and this is 1 minus PL2. And PL1, I need both works. So it is a P square, 1 minus P square. And this one PL2, I need both works. So this is another. Okay, so this is 1 minus P square, and plug in the value. 0.1, 1 minus 0.01, right? It is square of 0.1 and the square. It's 1 minus 0.99 square. What it is? 0.99 square. 9999, 9981, 9981, 9981, 9981, 110A9. Okay, 0.90 is a percentage 98. Yeah, like this. So we had a probability of the whole thing, whether the whole thing works. The probability is this one. Probability this one. So this is the whole structure is parallel, but each part of the parallel connection is a cascade connection, like this. We can also check another second example. I have two examples. This is a memory. This is M. Sorry. Memory model consists of 9 chips. So we have 9 chips. We have 9 chips. 9 chips. 9 chips. The device is designed the way redundant, so that it works even if one of the chips is defective. So I say B contains 9 chips, and the probability B works equal to B work equal to 9 works or 8 works. 9 work or 8 work. Yeah, the whole model work, the whole memory work if 9 chips work or 9 chips work or 8 chips work. Yeah, we have one even if one of it is defective. So this is a redundancy. So if one wrong, it still works. Okay, and each chip contains of n transistors and functions properly only if all of its transistors work. All of them work. Okay, so this is like this is the chip, and it contains n pieces connected with parallel, like a parallel, right? Parallel. Then you need all of them work to make sure the whole chip work, right? If anything wrong, then it will wrong. Totally how many? N. What is N? Just N. Okay, N is undetermined. N transistor. N transistor. Alright, now we have the problem. A. We want to know what is the probability PC of okay, this is C, sorry. This is C. C for the chip. This is the name C. Okay, what is the probability PC that the chip works? Oh no, this is chip. Yeah, this is B, still M, or this is another one. Second one is M. Okay. Sorry. It's M. M is memory. M has 9 chips, and each chip C has N transistor. And we want to know what is the property of C works. So C works equal to all of them works, and each works with probability P, right? Where it is. And transistors A probably B, probably B. So this is P to the n's, right? P to the n's. Okay. And the B, what is probability PM? PM, you say we have 2 cases, right? So equal to 9 chips work. So all of them work, or only 8 works. 8 work. Yeah. Okay, 9 works. All of them work. All of them, each one has this property. So 9 of them work is a P n to the 9th. Right? 9 of them work. And only 8 works. Only 8 work. So okay, so you have 9. One of it getting wrong. So you need 9, choose 1. That one getting wrong. It is 1 minus Pn. And all the others, they works. Okay, so this is the probability. We just studied this one last time, right? This one last time we studied this formula last time. And today, okay, now I have this. Then this will be what? This is a P to the 9n and a plus. This is it's just 9, right? 9 choose 1. 9 choose 1 is just 9. It is a 9 factorial over 1 factorial and 9 minus 1 factorial. So this is 9. Times 1 minus Pn and P to the 8n's. So this is a P 9 to the n's plus 9 times P to the 8n's and minus 9 of P 9n's. So it's 9 of P 8n's minus 8 of P 9n's. Anyway, yeah, so we have the probability of B looks like this. And okay, we have the third question, C. If P equal to 0.999, what is the maximum number of the transistors per chip N so that PM larger than 0.9? Okay, find N, maximum N, so that PM larger than 0.9, largest N. You can think, why is the largest N? When N increase, because P is a number smaller than 1. So when N increase, this probability will decreasing, right? Decrease if N increase, right? I'm writing this way. The Pn is this, and the PM is a combine of this PC, right? So each one has lower probability to work well. Then PM will also have lower probability to work well. So PM, this is also going down if N going up, right? PM is also like this. So when N going up, this probability will reduce, and we want to keep it 0.9. Okay, so we want to find the maximum N so that this one is larger than 0.9. Then how to calculate? Well, if you want to calculate by your hand, that will be a long work. You can use computer to do that. Just find the N, right? We can do that. Do that. Okay, here we have n. You can use a loop. You can use a how to use the loop. We can use them together, not loop. This is MATLAB. If you work in C, you have to check one by one. But now we're in MATLAB. I use n, run from, I don't know how many n it will work. Like I start from 1 till 100. Yeah, I just choose some n. This is n. And then I calculate this probability Pm. Probability of m equal to 9 times p. I need a p. P is lowercase p. P is 0.999, right? P is 999. P is 999. After 0, I have 3 nines. Yeah. P is 999. Then I calculated the probability of m equal to 9 times p to the, now is a dot. It's because the power is not one number, it's a vector. It is 8 times n. 8 times n, right? And minus, this is 8 times p to the dot to the 9 times n. Okay, I have a Pm. I want to find the value, which is yeah, I can plot it to see. Plot stem. Okay. St stem of this P. What do I have? Oh, not P. Right, the Pm, not Pm. Okay, Pm is the probability. You see, when n increase, n run from 1 to 100, and the probability is reducing, larger than 0.9 until somewhere. There will be somewhere here. What will be the value? 60 something. Okay, I do it again. No, it's n is around 60, right? I use 50 to if the 50 will be larger than 0.9, and the 70 will, I think 80 should be lower, right? 50 to 80, I think. I can try p equal to 50 to 80. I do the similar calculation. The Pm are equal to these, and then stem Pm. Okay, so where are we here? Okay, 30. So the first one should be 50. 50, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 60. I think it's 60. And this side, on the 20 place, this will be 70, 60 to 70. I mean, reduce the range from 70 to from 50 to 60 to 70. To 70, and the Pm and stem. Okay, I can list it, right? Just Pm. What is a Pm? All right, this is a 0.9. Here's a 0.89. So here, this one is according to the largest n, right? So this is a 60, 162. So 62 is the largest value. So yeah, I just working in MATLAB. My God. n equal to 62. 62. Yeah. If you do not have MATLAB, this one you still can work. It still works. You do calculation, but there will be a lot. There will be a lot. All right. If you are familiar with log, you can do this calculation with the help of log. Use the table of log. Use log. Yeah. But now we have computers, so just use computer. We can find this. We can find this. All right. Yeah. So each chip, you can have n transistors, but you cannot have too much. Too much. You have more, then you have more chance to get something wrong. Yeah. To get more chips here, you have more risk. Right? So you can use few. Well, it depends, right? When you want to build something, you need to consider not just the reliability. You also need to consider like the capacity or something else, right? Yeah. Okay, so this is one example, and we can consider another example. Okay, we'll go back to the power network. Suppose we have two plants. This plant 1, plant 2, power plant, right? Creating plant, plant 1, plant 2. And then we have the network looks like this. So this one go to here, this one go to here. They are connected, and you have home here. You have home here. You go from here. All right. Now we want to consider the probability you have power. You have power equal to 1. And we have some restriction. We have some probability. Suppose the P1 and P2 always work. So we only consider the case the wire getting something wrong. So suppose this one works. The probability work is this is a P1, this is a P2, this is P3, P4, P5. Okay, all of them are P. All right, P. Like this. This is a wire 1, wire 2, wire 3, wire 4, wire 1, 2, 3, 4, 5, and wire 6. Oh, we have six wires, six paths, right? And the P WI works. Probability of this one, or you can just write it as probability of WI. It is a P, the same number P, same number. The probability of each part is the same probability P to works. Then what is this one? So you need an analysis firstly. So P, I use B for this. The probability of B, that means okay, I say this is a P1, P2, right? P1. So P1 to home works, and P2 to home works, right? We have these two. We have two. Yeah, I write this. This probability of P1 to home work, or P2 to home works. You did home H to home works. So this is H. All right. We have these two. We need both works. Then this one will equal to, I say, the P of. I just write shorter. This is the P1 to home works, and P2 to home works, and a minus P1 to home works and P2 to home also work. You can write in this way. And P1 works. We have two paths, right? This is one path. This is another path. So P2, this is P2. P2 works. We have two paths. Actually, the two, you combine these two together. So P1 works, P2 works. You need a, how to say, P2 works. Yeah, P2 works. I can separate as three parts. This is one path, and here's a connection with parallel connection with 2, and then another one, right? So P2 as well P1 because you're similar. Okay, P2, P1 will be this one and plus P2. P2 works. P2 works is this. This is P. This is P. This is P because this is a parallel connection. So P times property of this times another P. And this part, because this is a parallel connection, I need to use 1 minus, both doesn't work. So W2 doesn't work is 1 minus P. W4 doesn't work, it's 1 minus P. This is a W4C, right? W4C. And here W2 and W4 doesn't work. So it's 1 minus P1, P2. P1, P2 is both works. Minus it is the whole thing doesn't work. So this is a W5, W4 and the W2 and the W5 doesn't work. W2 and W5 doesn't work. Yeah, this path W2, W5 doesn't work. Doesn't work. Okay, so this is this part, and then another P. This is W6 works. This is W6 works. This is W3 works. W3 work. W4 doesn't work. W4 doesn't work. This is W2 and 5 doesn't work. Okay, so the whole thing, this part is P2H. And similar here, that will be P times 1 minus P and 1 minus P1, P2 and P plus. So this one is here, still W6 works, and this one it is here, W1 works, and this part 1 minus P will be this one. This is W5. W5 works. The property of this W5C. W5 doesn't work. And this one is W2. W4 doesn't work. Right? Okay, these two terms. And I minus the intersection of these two. Intersection of these two, so this work or this work. And this works. So both works. Both works. Oh, this is complex. Both works. We have several cases. Alrighty. P1H and P2H. We have this is 1. It works. And this one. So this is both works, right? And this also both works. Right? The whole table is here. And totally we have 4. Symmetrically we have 4, right? And okay, so this one go this way and go this way, and this way work and this way work. So we have 1, 2, right? Each one you have 2 paths, so totally you have 4 paths, 4 combination. Okay, so the 4 cases, so here's broken, here's broken, here's broken, and here all of them are connected. So the probability, this one and this one, then we have 1, 2, 3, 4, 4 cases. And each case, actually these 3 are same. All the paths connected, only one is broken. Only one is broken. So it's just 3 of 1, 2, 3, 4, 5. 5 of them works. P means works, and 1 is broken, like this. And the last one, all the paths are work. All the paths have to connect it. So this is a P to the 6. All right. Then the final answer, that will be, okay, let me copy from here, is P, okay, PB will be 2 of that, that's the same, P times 1 minus P and 1 minus P1, P2, or P1, P2 are same thing, P squared, so P squared times P. And here, the minus this, minus 3, P fifths times 1 minus P plus, okay, plus is also fine, P6, right, it is. So the final answer will be this one. Okay, at any time, if you want, you can do simplify to see what it is. Alright. Okay, that's all for today. See you next time. Have a good weekend. Bye bye.